Hello there. In this video I want to provide an introduction to non-inertial frames by talking about the case of uniform acceleration. So before we get into that, let's just briefly discuss a little bit about why we even use non-inertial frames in physics, okay? Because we know that Newton's second law is only valid in the case of an inertial frame, or in other words, that you're observing the system in a frame that is not moving with a relative acceleration compared to another frame. Notice how I said that, with respect to another frame. That implies that I can come up with inertial frames for any situation. Okay, so let me introduce the concept of these frames or frames of reference to us with these examples here. So, first I have this car, and in this car we have a pendulum of mass little m. The car is accelerating to the right with an acceleration a. Now, I could put down an inertial frame of reference, okay? All I have to do is I just have to put my coordinate system outside of the car. I'm going to call this coordinate system I, or this frame of reference I, because it's an inertial frame of reference, okay? And it sees the car accelerating to the right. Next, I'm going to change perspectives. I want to view the perspective of somebody from within the car. So instead, I'm going to go ahead and put in a different non-inertial frame. I'm going to call it N because it's a non-inertial frame of reference within the car. And its origin here is locked with the car. So it accelerates to the right with the car. Now, why is N a non-inertial reference frame? Because it's accelerating with respect to our inertial frame I. Okay, so remind me real quick, which frame are Newton's laws going to hold? They're going to hold in the ith frame. And we're going to have to, if we go into the nth frame of reference, we're going to have to modify Newton's laws somehow. We'll talk about exactly how in a little bit here. Okay, but do you see that procedure of, look, I can define an inertial frame, then I define a non-inertial frame with respect to the first frame, which I know is inertial. And then I point out that there is some non-trivial relative motion between the two frames. Alright, let's do one more example. Here I'm trying to analyze the physics of a hurricane, right? So now, where would my inertial reference frame be, right? Because we're stuck on the Earth. Our perspective is here stuck on the rotating Earth. But if I want to create an inertial reference frame, I need to put my frame outside of the Earth, or in other words, not rotating with the Earth. My inertial reference frame would be here, and then our human perspective here on the Earth is stuck rotating with the Earth, and so we're here in a non-inertial frame. And again, there is some relative non-trivial motion between I and N. Right? We'll talk about exactly how the rotating reference frames changes things, but again, conceptually, which frame are Newton's laws going to hold in frame I? Which frame are Newton's laws going to break down, or we're going to have to modify Newton's laws in frame N, okay? The conceptual understanding is really important because as soon as you have the conceptual understanding, the proofs, particularly in the uniform acceleration case, this is going to be really fast. So let's go ahead and talk about uniform acceleration now. So let me go ahead and put down a particle of mass m here, okay? And I'm going to put down two different frames to analyze the motion of m from. First, I'm going to put in some inertial frame, and I'm going to call this I for inertial. And then I'm also going to consider M in a non-inertial reference frame, okay, which I'm going to call N. And the difference between the frame I and N is N has some acceleration, some linear constant acceleration, which I'm going to call A. Again, to be clear, this acceleration A is with respect to our inertial frame I. Now there might be a part of you that gets clever and is tempted to say here, oh ho ho, but I could also just as easily say that if I go into the N frame, this guy's still, and I is accelerating with respect to n. What's the difference there? Okay, and while it's tempting to do that in these kind of proofs where I and n are just so arbitrary, remember that at the end of the day, we're motivated by the physical examples like we had above, right? Where there is a very clear distinction of an observer that is stuck within an accelerating system and an observer in which we've pulled ourselves out of that accelerating system. Okay, so we need to make a clear decision here that no, I is going to be the inertial frame and n is going to be accelerating with respect to I. Alright, if we're feeling good about this, let's go ahead and track the position of our m particle in both frames, okay? So the way that we're going to do this is first, I'm going to go ahead and put in a position vector. I'm going to call this Rn. And this is going to track the position of m in the n frame. Next, I'm going to go ahead and put in another position vector. I'm going to go ahead and call this guy. I'm going to call you Ri. Let me finish this. Call this Ri. And you are going to be the position of, our particle m with respect to frame I. And next, let's go ahead and complete this triangle by connecting Rn and Ri. Okay, and I'm going to do this with this capital vector R. So capital vector R is the vector which connects our reference frames I and n to each other. All right, and to be super duper clear, right? Because sometimes this gets confusing with these static type images. Remember, everything in physics is in motion, right? So R can be a function of time, Ri can be a function of time, and Rn can be a function of time, and they will be functions of time if things are moving around dynamically, right? All right, well, in this specific example where n is moving with respect to I with a constant acceleration, what would that say about capital R? Okay, think about it. That means that R double dot is going to be equal to A, right? All right, pause and make sure that we understand that putting this constraint that n happens to have a uniform acceleration with respect to I, that is what defines this kind of constraint here on how our vector capital R acts, which we're using to describe the relative motion between I and n. All right, are we feeling good about that? Okay, if so, we know that in the inertial frame I, whatever happens to this mass is going to obey Newton's second law. So I'm going to suppose that, this m, it could have, some forces on it, right? Some net external forces on it. So in which case, in the inertial frame I, right, sigma f is going to be equal to m times Ri double dot, right? F equals ma. But look, you see how we have this triangle of three vectors here? So we also know that Ri is going to be equal to capital R plus Rn. Right? You see how the two vectors add tip to tail and they make Ri? So that means that sigma f we could also consider is equal to m times R double dot plus Rn double dot. All right, and so let me just go ahead and isolate this m times Rn double dot so that it looks like we have a situation like Newton's second law. So I'm going to have sigma f minus mr double dot is equal to m times Rn double dot. Do you see what we've done here very, very clearly? In this step, which I'm going to box in purple, we took our system, which we totally wrote out in our inertial frame I, and it obeyed Newton's second law. And then just like that, by using the step in purple, we've gone in and we've transferred this over to now we're saying, all right, so what are the dynamics from the perspective of n? and they look almost like Newton's second law, but now there's this extra term here, okay? And so our perspective in I and N are going to differ based on the relative motion between the two frames. Now again, in this particular example, let me go up to the orange, right? Let me box this guy in orange here, right? In this particular example, that specific relation between the motion of N and I, well, they're uniformly accelerating. So let's go ahead and, update this. So with our orange condition, in which case we're uniformly accelerating, then we have this kind of final statement here, which is that sigma f minus ma is equal to mrn double dot. All right, and I'm gonna go ahead and box this result here. By the way, let's be super duper clear about this result. What happens if the acceleration of frame n is 0? Oh, then this term here drops out, and we would be left with a situation where we just get sigma f equals ma again, right? Because our frame n is not accelerating, it's also an inertial frame, and so we get back sigma f equals ma. Great! But now, what I'm going to go ahead and lastly do is I'm going to define this term, this minus ma here, right? Because I want to rewrite this in a way that looks like Newton's second law, because it's going to make it really convenient and nice to analyze problems. So I'm going to define this minus ma term. You are defined as what I'm going to call a fictitious force, F fictitious, okay? And in which case we can go ahead and write this out one more time as sigma f, where now we're super clear that these are the actual forces that are acting on our mass m, plus some additional fictitious force, F fictitious, is going to be equal to mrn double dot. So in other words, if we look in the n frame, and I'll go ahead and do this pictorially in a second, if we look in the n frame, then all we need to do is we need to add in one fictitious force, okay, to the system, and we get back Newton's second law. So let's go ahead and do this. Let me go ahead and drag. We've defined our fictitious force as minus ma. So I'm going to take this guy here, and we're going to show exactly how we can do that. So what's that going to look like in this case? If we analyze things, right, from n's perspective, right, if n is accelerating in this direction with respect to I, and we look in the n's perspective, that means I need to put one more additional force in. I need to put in one more additional force here, and this force is going to be equal to minus ma. You notice how it points in the opposite direction, that n is accelerating with respect to I, okay? So this guy here, this is my fictitious force, okay? Let me really solidify this. Let's go back to the car real quick. So in the I frame, the acceleration is going to point straight to the right. And so if I want to view things in the n frame, what fictitious force do I need to add? I need to add in a fictitious force, which is going to point in, to the left here, and it's going to have a magnitude of ma. All right, and then from here, we'd be able to, go in and identify our other forces, like mg, like tension, and we'd be able to go through and solve this problem. We'll definitely do some practice problems going forward on non-inertial frames, but I think this is a nice introduction. If you enjoyed this video, found it helpful, let me know in the comments and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.